For decades, computer vision was a divided pipeline. Engineers spent years writing manual mathematical rules to extract features from raw pixels, and then fed those isolated features into a separate machine learning algorithm to categorize them. Modern deep learning replaced manual engineering with a continuous, multi-layered architecture. Instead of following human-defined rules, it transforms raw pixels into a hierarchical data structure. In this end-to-end pipeline, the network learns to identify and classify objects simultaneously. By calculating the error at the very end of the model and passing that information backward through backpropagation, the network jointly optimizes both the feature extraction and the final prediction. This creates a step-by-step hierarchy. The earliest layers act as simple filters to detect basic lines and color gradients. The middle layers combine those lines into complex textures or specific object parts, like a wheel or an eye. By the deepest layers, the network is assembling those parts to recognize complete semantic concepts, like a car or a dog. True machine vision required giving the architecture the capacity to automatically discover the most efficient way to process raw pixels, bypassing the strict limitations of human intuition. The catalyst for this shift was the ImageNet Large-Scale Visual Recognition Challenge. It was a massive benchmark, demanding that models correctly categorize over 1 million images into 1,000 highly specific object classes. Because an image might contain multiple objects, the competition used a top 5 error metric. A model's prediction avoids an error penalty as long as the true label appears anywhere within its 5 highest guesses. This chart tracks top 5 error rates against winning network depths. Errors plummeted from 28% to under 4% as architecture scaled from 8 to 152 layers. This depth acts as a structural constraint, forcing the model to generalize visual principles rather than memorizing training samples. But this introduces a major engineering paradox. Deepening a network exponentially increases the demand for computational power and GPU memory. The breakthrough was not a matter of brute force hardware, but the mathematical optimization of the model's internal parameter footprint. This equation shows why you cannot process an image using a standard fully connected layer. If you take a small 200 by 200 pixel image and connect every single pixel to a 40,000 neuron hidden layer, you generate exactly 1.6 billion trainable parameters for just one single layer. A layer this massive exhausts available GPU memory. Worse, it flattens the image into a 1D vector, destroying the spatial topology that relates neighboring pixels. A model with over 1 billion parameters on its first layer guarantees catastrophic overfitting on almost any dataset. The solution is the convolutional layer. Instead of connecting every input pixel to every hidden unit, a convolutional layer relies on localized receptive fields, observing only small, specific patches of the image at a time. This visual demonstrates the mechanical process. A small 3D matrix of weights, called a filter kernel, is overlaid onto the corner of the input volume. It multiplies its weights against the overlapping pixels and accumulates the result to produce a single scalar value in a new activation map. The filter then moves by a set stride, usually 1 or 2 pixels, and repeats this multiply-accumulate operation. It sweeps across the entire width and height of the input until it generates a complete 2D activation map representing one specific visual feature. A single filter only identifies a specific pattern, like a vertical edge. To recognize multiple features, we deploy dozens of separate, independent filters simultaneously. Each one creates its own activation map, and these maps are stacked together to form a multi-channel 3D feature volume for the next layer to process. Inside a deep architecture, this data travels through a rigid pipeline. The convolution extracts spatial patterns, a normalization step scales the values, and a ReLU activation function injects nonlinear logic by clipping negative numbers to 0. Finally, a pooling operation evaluates local windows to shrink the spatial dimensions of the grid. Because a convolutional layer relies on weight sharing, reusing the exact same small filter array across the entire image space, it extracts complex spatial patterns with a tiny fraction of the computational footprint demanded by a fully connected network. To evaluate exactly how efficient these layers are, we use this parameter equation. The total trainable weight count is the number of filters multiplied by the depth of the input volume multiplied by the filter kernel's spatial area. Early deep learning models utilized massive 11 by 11 filter kernels in their first layers. Because the spatial variables scale quadratically, using large filters caused the parameter footprint to balloon, limiting how deep the network could actually be built. The VGG-net architecture solved this constraint by abandoning large filters. It enforced a strict structural rule. The network would only ever use uniform 3 by 3 filters with a stride of 1 throughout its feature extraction phase. This comparison shows the logic of effective receptive fields. Sequentially stacking 5 small 3 by 3 convolutional layers observes the same total visual area of the original image as a single 11 by 11 layer. The math dictates different hardware requirements. A stack of 5 3 by 3 layers drops the parameter count from roughly 23,000 down to 8,600, using nearly 3 times less memory to process the exact same spatial footprint. There is also a compounding structural advantage. Because every convolutional layer passes its output through an activation function, the deeper stack injects 5 independent ReLU activations into the data path. This density of nonlinear logic allows the network to learn complex, hierarchical patterns. Increasing network depth using stacks of small filters is a structurally superior method for learning features and a mathematical necessity for computational efficiency. The 22-layer GoogleNet architecture took this optimization even further. Instead of a purely sequential line of layers, it processed features using distinct parallel blocks known as inception modules. This diagram maps the data flow through an inception module. The input from the previous layer splits into 4 parallel branches, including 3 by 3 and 5 by 5 convolutions, before their resulting feature maps are stacked back together at the end of the block. This creates a computational thread. Running large spatial filters across an input volume that contains hundreds of channels simultaneously will cause the required mathematical multiplications to explode beyond hardware limits. GoogleNet solved this by inserting additional 1 by 1 convolutional layers directly in front of the heavy spatial filters to act as bottlenecks. A 1 by 1 convolution applies a filter to a single spatial pixel coordinate, but because the filter must match the depth of the input, it computes a dot product straight down through all the channels at that coordinate, collapsing it into a single scalar value. By configuring the layer to use a small number of filters, the network forcefully compresses the channel depth. A tensor that arrives with 200 channels is squeezed through the bottleneck, emerging with only 30 channels, while its spatial width and height remain untouched. The impact on efficiency is massive. Because the subsequent 5 by 5 filters now operate on a heavily compressed input depth, the total required weights for the operation drop from 250,000 down to 43,500. This is the bottleneck paradox. Inserting additional convolutional layers into an architecture can decrease the total volume of mathematical operations, provided those layers operate strictly as dimensional compressors. Even with efficient convolutional layers, early networks faced a final structural trap. Flattening the spatial map into a 1D vector and passing it through dense, fully connected layers accounted for the majority of the model's total parameters. To keep its footprint minimal, GoogleNet replaced these dense stacks with a mechanism called global average pooling. This diagram illustrates global average pooling. Instead of unraveling data, the network averages every spatial pixel within a channel map into a single value. A 7 by 7 tensor condenses into a lightweight one-dimensional vector containing one value per channel. Bypassing the flattening step eliminates millions of connecting weights. By applying global average pooling, the parameter count for the terminal classification stage drops from 50 million down to 1 million. That final pooled vector is passed through a single linear layer, projecting the features into the 1,000-dimensional space, representing the ImageNet categories. This flowchart tracks the softmax layer. Unnormalized logits pass through an exponential function and are divided by their total sum, creating a probability distribution summing to 1. If this prediction deviates from the true label, cross-entropy generates an error signal initiating backpropagation. Superhuman visual performance was achieved through precise tensor operations, deep 3 by 3 stacks, 1 by 1 bottlenecks, and global average pooling. Modern neural architecture is ultimately an exercise in applied mathematics, optimizing for depth under strict resource constraints.